We shall be doing angular momenta, addition of angular momenta, and in particular Clebsch-Gordon coefficients, how to calculate them, and see one or two examples, and then we will see more examples in the tutorials or these assignment problems. So, just to remind you that we have looked at angular momenta which are like this L, which is called as the orbital angular momentum, and then we have also looked at spin angular momentum, and then we also have looked at J, which is the total angular momentum, and J becomes an important quantity when there are these L couples to S, which is called as a spin orbit coupling. And in each one of these angular momentum, these variables, they have different relations, like the relations are mostly expressed as L cross L is equal to I h cross L. That is a commutation relation, which means that any of these Li Lj, the components of the angular momentum, which has a relation which is say I h cross epsilon I j k L k. In case we have missed an H cross, it really does not matter. I mean, sometimes H cross is put equal to 1, but nevertheless it is important because it sets the scale for the angular momentum. And similarly, we have S cross S, that is equal to I H cross S, and similar relationships follow as well, that it is S I S j commutator is I h cross epsilon I j k. Now, this epsilon I j k, we have explained that before, it is called as a Levi-Civita symbol. If it is clockwise, that is I j k maintaining an order, then it is equal to 1. If you flip any of the pairs, that is I and j, if you make it j and I, then it picks up a negative sign, and if any of the two indices are made equal to same, then the Levi-Civita symbol, that is epsilon I j k, is equal to 0. And this is all told, and so j is equal to L plus S, and this is equal to I h cross j, and we have this j I j j, which are two different components, which is again epsilon I j k, and so on. Okay. So, these are the commutation relations that we have seen. Now, we talk about addition of angular momenta, and in particular we will just talk about J, but these addition rules, they are sort of valid for all these other two angular momenta as well. So, we will talk about addition, and these addition means that we are talking about J equal to J 1 plus J 2. So, these are two particles. So, 1 and 2, they correspond to two particles. So, we have these the total J is equal to a sum of J 1 and J 2, and this quantum number corresponding to J is called as a J, and the quantum number corresponding to J 1 is called as a J 1, the small j 1, and j 2 corresponds to a j 2, and similarly the j z, that corresponds to m, j 1 z corresponds to m 1, and j 2 z corresponds to m 2. So, these are the notations that we have, and we will see that what these Clebsch-Gordon coefficients mean in the context of these addition of angular momentum. Now, it's true that the vectors, the j vectors, they actually commute corresponding to the two particles, but there is a problem that j square actually does not commute with either j 1 z, or it does not commute with j square and j 2 z, and this is not equal to 0. So, either of them is not equal to 0, because the j square contains a j 1 square plus a j 2 square, plus there is a 2 j 1 j 2, and this 2 j 1 j 2 will have terms such as j 1 x, j 2 x, J1y, J2y and J1z, J2z. Now, of course, the z component will commute with this J1z or J2z, but the x and y components will not commute with these with this J1z or J2z, and that is why these commutation relations are not equal to 0. And so, let us say talk about this eigenfunctions corresponding to J1 and J2. So, these eigenfunctions are so this corresponding I mean, and the first one, that is J1 is equal to J1 M1, which is what we have said just in the last slide, and this for the J2, this will be like a J2 M2. If you are a little more careful, because we have this M, the magnetic quantum number, that takes values minus J2 plus J, or here M1 will take minus J1 to plus J1, but there are these M's corresponding to the L, that is the orbital part, and then the spin part, and then this J part. So, here this is what is called as M here. So, we are really talking about J, the total angular momentum vector. So, we are using this Mj to be equal to M, but remember that if you really want to deal with all three of them, it is best that the magnetic quantum numbers carry their respective indices, which are either L, S or J and so on. Alright. So, this J1 this takes values which are this corresponding to this. So, the M1 will, so J1 will have some values which are integer values, and then M1 will have values which are from J1 minus of J1 to plus of J1 through 0, and M2 will have values which are minus of J2 to plus of J2. Let me put the plus sign explicitly, and through 0. So, it is like minus J1 minus J1 plus 1 minus J1 plus 2 and all the way to 0, and then so this all the way, all this is equal to plus J1. So, this will be equal to the one that is before that is equal to J1 minus 1 and so on. So, this will be like 1, 2 and all that. Okay. So, these are the values, and similarly for M2. So, these are the values for M1, and similarly you will have values for M2. Okay. So, so we basically we can construct product state for this composite operator. So, we will just tell you what it mean by product states from the single particle states. And in some sense there is no interaction between these two particles that we are considering, and that is why we can construct these product states. Okay. So, what we mean by product states is the following. So, we have corresponding to particle 1, we can have a J1 M1 and written as a ket, okay, and this is going to be multiplied by J2 and M2, that is another ket, and there is a product, you can write it like this, and this can be written as a composite state, or like a product state has a representation which is like a J1 M1 J2 M2. You can put a comma in between in both the sides between the indices. In fact, it is probably a good to put a comma everywhere, so that we know that these are distinct indices, J1 M1 and J2 M2. So, what we have is the following, that we have this J1 square, this is that thing acting on J1 M1 will give us a J, and it is for the product state as well. I mean, this can be written as the complete composite states J2 M2, and this is equal to J1 into J1 plus 1 H cross square, and then it gives you this J1 M1 J2 M2. Okay. And similarly for the J1 Z, on acting on this J1 M1 J2 M2, this is equal to M1 H cross and then J1 M1 J2 M2. Okay. So, that is very clear, and some similar relations for J2. J2 and J2Z, or J2 square and J2Z, you can write that. Okay. So, now what we do is that, so let us work with the composite state. So, it work with that, and if you do that, then let us write down the composite operator, which is equal to J1Z J2Z, and let us see what that is. So, J1 M1 J2 M2. Okay. So, this is equal to a J1Z plus a J2Z, and acting on this J1 M1 J2 M2, and this is equal to M1 plus M2 H cross J1 M1 J2 M2. What I am trying to convince you is that this composite state that we have formed is a good description of the problem, or is a good basis, or it can be called as an eigen basis for this problem that you have in hand, that is to work with this angular momenta, the total angular momenta comprising of these two particles. So, this is a sort of basis that makes sense to us. Okay. And now, you also sort of you can write it as the J square acting on these. So, J square is, if you want to act on these J1 J M1 and J2 M2. Now, that is not equal to say H cross square. If I take common, it is not equal to J1 into J1 plus 1 plus J2 into J2 plus 1 and these state. So, this is incorrect. So, this is not correct. So, if you write an equality, then it will be incorrect. The reason is that we have told that for this J square, your this basis is not a correct basis, okay. But it works fine for these each of these J1 square and J2 square and J1Z and J2Z. The reason that this is not a good basis is that if you expand the J square, this is equal to a J1 plus a J2 whole square, and this will give us a J1 square plus a J2 square, for which it will work fine, but not for the 2 J1 J2. Now, J1 and J2 commute, that is why we can combine the cross terms J1 dot J2 and J2 dot J1, they can be combined and we can write a 2 J1 dot J2. Now, this term is the problematic term, because of which these basis is not sort of an appropriate basis. So, now if that is the case, we have these terms, the 2 J1 J2, let me write it explicitly. So, this is equal to let us forget the 2 factor at the moment, but we have a J1 x J2 x plus a J1 y J2 y and plus a J1 z J2 z, and this does not seem that these two are going to do not commute with either J1Z or J2Z. Okay. So, that is the problem. So, J square does not commute with J1Z and J2Z. So, let me write that down, that is important, does not commute with J1Z and J2Z, okay, and it is an important thing for us. So, this emerges two descriptions. What is the other description now in case? So, we have looked at one description J1 M1 J2 M2. This is one description, but there is another description that is going to work for this thing, which is like a J1 J2 a JM, right. That is going to work. This is also a good description or good basis of the problem for this total angular momentum of two particles, okay, the sum of the angular momentum. This is also a good basis. And why is this a good basis? This is a good basis because your J square would acting on this J1 J2 Jm, this is going to give us a J into J plus 1 H cross square and returns me this basis J1 J2 Jm, and also my the total this J1Z and J2Z, the sum of that is, which is J1 J2 Jm. This is equal to sort of M H cross and J1 J2 Jm. So, if I forget giving this comma, please do put them. So, this is also a good description. This is exactly what I said, and we have also shown earlier that this is a good description as well. That is J1 M1 J2 M2, and now we see equally a good description that J1 J2 Jm. So, these quantum numbers, the quantum numbers J1 J2 M1 M2 as well as the quantum numbers J1 J2 Jm, both are the real eigenbasis, so to say, for this problem comprising of this J, which is the sum of the two angular momenta of the two particles. Okay. So, for this once again this is a bit of repetition that I am doing, but it is probably worth it because you need to understand these well. So, this is equal to J1 square J2 square, these are the operators, okay, and J1Z and J2Z. So, these are the corresponding operators, and a J1 J2 Jm, we have these as operators J1 square J2 square, total J square and total Jz. Okay. So, these are the operators and these are their eigenvalues, both seem to be satisfying or both are good descriptions. Okay. Now, if for a given problem there are two descriptions which are equally valid and they are they are the eigenbasis for the problem, then there has to be unitary transformation that connects these two bases. Okay. And these unitary transformation, just let me remind you that if there is a unitary operator which connects say a vector to another vector, say u y, and then you have this u dagger u, this is equal to 1 or u dagger is equal to 1. So, we should have a unitary transformation connecting the two descriptions of the system. If there are two distinct descriptions that are possible, they should be connected by a unitary transformation, and this unitary transformation takes us to what we know as the Clebsch-Gordon coefficients. Okay. All right. So, we'll tell you what these these physical meaning of these Clebsch-Gordon coefficients mean, but let me just sort of take you through this, that what are the allowed values of all these quantum numbers, because these are important. We have told for some of them, like for example, M1, it starts from this, we have written it explicitly, I am just repeating it here for completeness. So, it is a J1 minus 1 and it goes to minus J1, okay, or you can write it from the other way around as well. And M2 is simply that J2 and J2 minus 1 and then the last term, or if you start from the other side, it is the first term. So, that is your the two values. Okay. So, these are the two magnetic quantum number values, and M of course also goes from minus J, or we can write it the way we wrote it here. So, it is J minus 1 all the way to minus J, and what about the total this J? So, J will take values equal to J1 plus J2, J1 plus J2 minus 1, and it will have values which are J1 minus J2, but you have to take the mod because it takes only positive values, and so whichever is larger, it does not matter. I mean, the difference between that and you take a difference and then you can take a mod of that. Okay. So, what we are trying to do is that we are trying to build up a connection between these two descriptions, and let me write down the description that we wrote later. So, it is a J1, J2, Jm. That description has to connect to for all possible values of M1 and M2 subject to the condition M1 plus M2, this is equal to M. And then we have these this J1 J2, that is the other description that we have said that. So, it is M1 M2. Now, you have to of course use this coefficients, and that coefficients are known as this Clebsch-Gordon coefficient. So, that is a J1 M1 and a J2 M2. I hope that is the way we have written. We have written it, yeah. So, it is J1 M1 and J2 M2. So, J1 M1 and J2 M2. Okay. So, this is where J1 J2 Jm. Okay. So, so what we have done is that we have introduced this this vector, and we have really written down something that is nothing but 1, the outer product of this basis kets, and then of course, we have to do a sum M1 and M2, which takes values from minus J1 to minus J2 and so on, subject to the condition that the total M has to be the sum of these individual magnetic quantum numbers, that is M1 and M2. This thing this is called as the Clebsch-Gordon coefficients. We can call it a CM1 M2 because those are the things that are summed over, and these are the Clebsch-Gordon coefficients. We will write in short Clebsch-Gordon CG coefficients, and this is what we want to find out. So, you see that the left has one description and the right has this description. So, it is a connection between this description and this description, and the coefficient is what you need to find out, and these are called as the Clebsch-Gordon coefficients. Okay, so let me draw a table which will probably be simpler for you to understand that what we are trying to do. Let us take for j equal to J1 plus J2, right. That is the maximum value, we have said that here. it is J1 plus J2, that is the maximum value, and the minimum value is J1 minus J2. So, this is the maximum value. Okay. So, we have let us take these values of m and take these values of so this degeneracy is what we have, but then we have these m1 and m2 all possible values of m1 and m2. So, let us start with this corresponding to this j equal to j1 plus j2. The maximum value of m would be j1 plus j2, because m goes from minus j to plus j. So, the plus j is the largest value, which is equal to j1 plus j2. So, what can happen to this m1 and m2, and they have to be simply equal to j1 and j2. So, this is just one pair that will satisfy, because m1 plus m2 equal to m, and so this has a degeneracy or degeneracy of these terms. This is equal to 1. There is just one kind of terms that you can get. Let us see what is the next one, right. I mean, it is clear that there is a degeneracy equal to 1, because there is no other way you can choose your m1 and m2 values such that the sum of them gives you the value which is j1 plus j2, which is the maximum value of m corresponding to this maximum value of j, which is equal to j1 plus j2. Let us say the next value of m. So, the next value of m is j1 plus j2 minus 1. It can come from two ways, I mean two more ways than what I just show, which I will discuss in just a while. So, it is a j1 minus 1 and j2 is 1, and you can also form it by j1 and j2 minus 1. So, it has a degeneracy 2 at this moment. Okay. So, there is no further terms say. So, m has taken the next lower value, which is j1 plus j2 minus 1, and if you have to choose m1 and m2, because why you have to choose m1 and m2, let me just go back to the expression. You have to calculate this c m1 m2. So, different choices of m1 m2 you have to find out, and then take a linear combination of that in order to get this CG coefficients or the Clebsch-Gordon coefficients. Let me show you the next ones, which is j1 plus j2 minus 2. Okay. This can be formed by three ways, because j1 minus it is say 2 j2, you can have j1 minus 1 j2 minus 1, and you have j1 and j2 minus 2. So, there are three ways of doing this. Okay. And if you really go down to all the combinations, and for this value of j, which is written above the table, so the last value that you get, or the lowest value that you get, is j1 plus minus of j1 plus j2. And that again has just one combination, that is minus j1 and minus j2, and this has again this degeneracy equal to 1. So, this table will for this maximum value of j, so which will be given to you, I mean you will be given a state, and the state you will have to find out that what are the linear combinations of this state, and the CG coefficients will make sense, because they will give you the probability, or rather the probabilities for the state to be found in one given quantum state, defined by all these j1, j2, m1, m2 and so on and so forth. Okay. So, this is so we have taken the maximum value of j and then have done it. You can do the next value of j and can again form a similar table. Okay. So, let us call this, you can keep calling it a ket, but we just want to sort of simplify a little notation there. instead of writing all these commas etc. So, let us call this J1, J2, Jm to be a function, wave function, or this eigenfunction is J1, J2, Jm. Okay. So, this let us call this. Okay. So, we are going to write a J1, J2, M1, M2. Okay. This is equal to a psi of J1, J2, M1 and M2. So, if you look at it here, where we define these CG coefficients, we have defined these as J1, J2, Jm, but we can also write down a J1, J2, M1, M2, or let us follow the order in which we J1, M1, J2, M2, and then you can do a summation over M, and you can write this down as J1, J2, Jm. This is equal to, so this is a J1, J2, Jm, and this is equal to a J1, M1, J2 and M2. Okay. So, these will be the the Clebsch-Gordon coefficients, because this description is connected to this description. And now you have M1 and M2, so you have to sum over M, which is the summation over M1 and M2. In any case, you can call either of them as phi or psi, and because there is a description that is going to matter and so on. So, your phi of J1, J2 and J1 plus J2, J1 plus J2. So, that is the maximal state. This is equal to J1, J2 and J1, J2. And this is J1, J1, J2, J1, J2, J1 plus J2, J1 plus J2, and then you have this psi, which is J1, J2, J1, J2. Okay. So, we are writing the maximal state. So, J1, J2, and then we have this J1, J2. Okay. So, we are writing this maximal states and so on. Okay. So, both phi and psi, they are normalized to unity. Which says that all these things, that is J1, J2, J1, J2, these are the values for M1, M2, but for this particular state we are taking the maximal state, and we have a J1, J2, J1 plus J2 and J1 plus J2. This is equal to 1. So, this is the the sort of normalization condition, and now I mean you go to this next one in the table, and then you take this J1 plus J2 minus 1, which is the next state, and that is the next lower value of M. Then there are two possible values of M1 and M2 that you can construct, and that will give you this degeneracy of 2. So, you can write again these phis and psis, and they being normalized and so on, you can write them down, and so connect these phis and psis, and you can define them basically for that state. Okay. So, for that next one, at least do this for the next one, next lower value, so to say, of j, which is equal to, so M is equal to J1 plus J2 minus 1, and this tells you that this M1 can be equal to J1, or M2 can be equal to J2 minus 1, or it is the other way around. So, M1 equal to J1 minus 1 or M2 equal to J2, that is possible. Okay. So, we have these phi's, J1, J2 and J1 plus J2 minus 1, that should be a linear combination of. So, it is a linear combination of these two things which are given by these combinations. Okay. So, these should be combinations of psi J1, J2, J1, J2 minus 1. I am forgetting giving these commas, but you can give these commas, and psi J1, J2, J1 minus 1 and J2 and so on. Okay. So, these are the linear combinations that so there are going to be two Clebsch-Gordon coefficients which have to be found. We will give an example of that. Now, there is one more thing that we are missing here. What happens when your M or rather your J, next value of J, that is J equal to J1 plus J2 minus 1. So, that is next. So, this value, so this is the next lower value of J. We were talking about values of M, different values of M here, but kept the value of J to be equal to the maximum value. But J will also vary from J1 plus J2 to J1, the next value would be J1 plus J2 minus 1, and it will sort of decrease. Ultimately, you would reach J1 minus J2 mod, and that is the last value that you have. Okay. So, this J takes all positive values, and we are going to find out for that one. Now, for J equal to J1 plus J2 minus 1, the maximum value of M will start from the second value, because that is the value of, that will be the maximum value of M for J to be J1 plus J2 minus 1. And for that you will have these two combinations once again. So, all these this latter set would come from, not from this J equal to J1 plus J2, but the latter set will come from the J equal to J1 plus J2 minus 1. Okay. And that would actually sit at the top of the table, this table. Okay. When we change to, so what I am trying to say is the following. So, if you make another table and so on, now with J equal to J1 plus J2 minus 1 and all these M values and all these kind of degeneracies that you say, and all these M1 and M2 values. So, if J is this, the maximum value of M is J1 plus J2 minus 1, and then we can have M1 to be J1 minus 1 and J2, or we can have it a J1 minus 1. In fact, I should write and, because there is a linear combination, J1 comma J2 minus 1. Okay, and which has again a degeneracy 2. So, this sits at the top of the table, just like we have constructed the other table and so on. So, the next one will be J1 plus J2 minus 2, and that will have 3 combinations and so on and so forth, which is what we have written down. Okay. So, this, if you need me to complete this, then this is equal to a J1 minus 2 J2 and a J1 minus 1 J2 minus 1 and J1 and a J2 minus 2, and this has 3 degeneracy and so on. This is not coming from the maximal value of J, but it is coming from the next lower value of J. And in fact, this state that you get, this J1 plus J2 minus 1, you can actually operate the J, this thing on to this J1, J2, Jm, and you can get this state. Okay. So, a lowering operator can be operated on these things to lower the value of these maximal j from this maximum value reduces by 1 unit. I will write down the results for, or rather what happens when you apply j plus or j minus, which is called as a lowering operator for the angular momentum. Okay. So, I think it is clear that these combinations will have to be taken, and there will be again combinations when you have a j 1. So, if your j is equal to j 1 plus j 2 minus 2, then your m, the maximum value of m, let us call it m max, will be j 1 plus j 2 minus 2, and will be the third term which we have written down earlier. The term that you see here will be there at the top of the table, that is in place of this j 1 j 2. Okay. So, that will be threefold degenerate and so on. So, what are these? So, let me sort of simplify this description, or I mean this notation seemed to be sort of best to me, that this makes these quantum numbers to be explicit, and that is what is important for you. So, we have two sums m 1 and m 2, and the only thing that you need to sort of take into account is m 1 plus m 2 has to be equal to m, and we have a c m 1 m 2, that is the Clebsch-Gordon coefficient, and that is equal to j 1 m 1 j 2 m 2. Okay. So, that is the, so what does this C m 1 m 2 represent? What do these Clebsch-Gordon coefficients physically mean? Do they mean anything? Yes, do they mean something? So, these mod square is equal to, so this is the probability that at fixed values of j 1 j 2, or in fact, it is at fixed values of j and j z, that is more the way we are writing it, j and j z measurement. So, if measurement is done or measurement finds a particle, maybe an electron with j 1 z and the other. So, finds one particle with j 1 z, this z component of the angular momentum, and the other one with j 2 z. Okay. So, this is the meaning of the Clebsch-Gordon coefficient. So, if at fixed values of j square and j z, if you make a measurement on the particles, the individual particles will be found in their, the corresponding magnetic quantum numbers of them will be m 1 and m 2, and this is what it is. All right. So, let me give you an example. Let us take a state, say for example, okay, before that let me just write down this j plus minus, which I may not have written down earlier, but you can find it in any book. So, it is h cross and square root of j into j plus 1 minus m into m plus minus 1 and j m plus minus 1. This for individual particles. So, if you apply a raising operator, it will have a plus sign here inside the bracket within this m term, the second term, and it will also raise the state or the quantum number of the state, the magnetic quantum number of the state by 1, and if you apply j minus, it will lower the value of m in the square root to be by 1, and it will also return you a state which where the m value is decreased by 1. So, definitely these j plus minus they do not have J and M to be their eigenstates, or J in the other way around, J and M are not eigenstates of J plus minus, whereas they are eigenstates of J square and Jz, but these are important for us. Okay. So, an example, let us take an example, and simple example. So, let us have a J1, J2, Jm given as 1, 1, 1, minus 1. Okay. So, these are the values that are given, and now you have to find the corresponding J1, M1, J2, M2, and which all combinations of M1 and M2 will give rise to this state. That will give you the coefficient, and the mod square of the coefficients will give you the probability of finding them to be in those states. So, it is very clear that M, which is equal to M1 plus M2, it is M1 plus M2, this is equal to minus 1. Okay. So, this can happen from M1 equal to 0 and M2 equal to minus 1, or it can happen from M1 equal to minus 1 and M2 equal to 0. Okay. This will give rise to a possibility in which we can write this J1 M1. So, this is J1 is 1 and M1 is 0, and J is of course 1 and M is of course 1, and this will be 1. So, this will give rise to a state where in terms of J1 M1, J2 M2. This is this J2 and M2. So, these are these 1 and minus 1, that is fine, and this one will be 1 minus 1 and 1 and 0. So, these are these combinations. So, we will have to take a linear combination of that to express this state for a fixed value of for a fixed value of J and M. Okay. That is a total these angular momentum quantum number J and M, and these will consist of two such terms. So, we have this 1, 1, 1, minus 1, sort of a little sloppy in writing these commas, but you can put them there. So, we have this as C 0 minus 1, this C M1 M2. So, this is M1 and this is M2, and we have these 1 0 1 minus 1 and C 0 minus 1 or minus 1 0. This is equal to 1 minus 1 1 0. Okay. So, this state can be written the given state. So, this is a given state for a fixed value of J and M can be written in terms of these states with M1 and M2 to be given by this and the C M1 M2. So, since we have summed over all the possibilities, there is no sum left, but C 0 minus 1 mod square will tell you that we get M1 equal to 0 and M2 equal to minus 1, and C minus 1 0 will tell you that mod square of that will tell you that we get a state which is equal to M1 equal to minus 1 and M2 equal to 0. Okay. So, what we do, how do we calculate these coefficients? So, we still have to calculate C 0 minus 1 and of course, mod square is one thing, we have to first find these things. Okay. So, C M1 M2 that you have to find. And how do you find that? We can find it by these lowering operator, and the lowering operators are sometimes helpful, sometimes the raising operators are helpful, depending upon whether you just one above the lowest value, then you use lowering operator to make it 0. If you are just below the maximum value, then you use a J plus and make it equal to 0, because you cannot increase it beyond that. So, if you are in a you are in a maximally aligned state, that is the maximum value of J, then you use a j plus to make it 0, and if you are at the minimum value, then you make it operated by a j minus, so that it becomes 0. Now, you see that for this particular problem, when you have j equal to 1 and m equal to minus 1, we are already at the minimal state. So, you put a j minus, that will become equal to 0, because you cannot lower for a given value of j, which is 1, you cannot have anything, the m value, the total m value cannot be anything lower than minus m. So, that is what the idea is, and then you operate it on this minus 1, and that is equal to 0. So, this is given by j 1 minus plus a j 2 minus, and this is equal to C 0 or the way we have written it, yes, C 0 minus 1, and then we have these 1 0 1 minus 1, that is a j 1 m 1 j 2 m 2 plus a C minus 1 0, and we have 1 minus 1 1 1 0, and so on, and this is equal to 0. So, you have to operate that, and if you do that carefully, so you will have a j 1 minus and j 2 minus, and use this relation for these individual. So, remember that this is j 1 m 1, this is j 2, this is m 2, and so on, the same thing, j 1 m 1 and j 2 m 2, and so on. So, we have this j minus operating on 1 1 1 minus 1, that gives us a root 2 and gives us this. So, this root 2 operating this j minus on these things, or j 1 minus and j 2 minus, which is C 0 1 minus plus C minus 1 0, and will give us this state, which is 1 minus 1 1 minus 1, and so on. And this, if you put equal to 0, then you have a C 0 minus 1 is equal to C minus 1 0, and C 0 minus 1, and so this root 2 comes from that square root that you have here, this square root. Okay. So, this C 0 minus 1 is equal to minus of C minus 1 0, and so on. So, this tells you that these Clebsch-Gordon coefficients C 0 minus 1 equal to 1 by root 2 equal to minus C minus 1 0, and so on. So, that means that there are equal probabilities, because these two mod square is equal to half, there are equal probabilities to find m m1 m2 in the 0 minus 1 minus 1 0, and so on. Okay. That is what so, this is a way to find the Clebsch-Gordon coefficients, and let us take another example. And so, this I find the Clebsch-Gordon coefficients, a second example, and so let us say the state is given as 1 1 2 0. So, which means that j 1 equal to 1, j 2 equal to 1, j equal to 2, and m equal to 0. Okay. So, m 1 now can go from minus 1 to plus 1, that is basically minus 1 0 and plus 1, and m 2 also can go from minus 1 to plus 1, which means minus 1 0 and plus 1, and then subject to the condition that m 1 equal to m 1 plus m 2. So, all these combinations of m 1 and m 2 has to finally give you a m equal to 0. So, what we do is that we write a slight bit of okay. So, we can write the full notation, this j 1 j 2 j m, which is equal to my the Clebsch-Gordon coefficient C m 1 m 2, and then we have these J1, M1, J2, M2 and so on, and then sum over M1 and M2 subject to the condition that M1 plus M2 will have to be equal to M. So, let me only use the relevant things. If you allow me to just shorten the notation, this will be like C M1 M2, this will make it a little simpler notation, J1 M1, and the other one will have just J2 M2. So, then we have this is a shorthand notation. So, I go from this to this notation. So, little change in notation and little bit of shorthand notation. So, we have 2 2 which is equal to C 1 1 1 1 1 1. So, the A1 M1 are 1 1 and J2 M2 are 1 1 as well. So, that is a 2 2. Now, we have these 2 1, this is equal to C 1 0 1 1 1 0 and C 0 1 to be equal to 1 0 and 1 1. That is 2 1. Let me write the 2 0. Okay, we can write because 2 0 has many terms. So, we have these 2 0, that is J m equal to 2 0, that will be equal to C 1 minus 1 1 1 1 minus 1 plus C minus 1 1 1 minus 1 1 1 plus C 0 0 1 0 1 0 okay. 1 0 plus C again a 0 0 will be equal to 1 0 1 0. Okay, so, there are 4 terms there, and so this is equal to a C 1 minus 1 and 1 1 1 minus 1 and a C minus 1 1. So, 1 minus 1 1 1 and plus this is really 2 0 0 1 0 1 0. Okay. And so, if you normalize it, it becomes, because there is 1 here, there is 1 here, there is 2 there. So, 1 plus 1 square plus 1 square plus 2 square, which is 4, is 6. So, this comes with a 1 by root 6, and then we have this 1 1 1 minus 1. And so, I hope this 0 0 is clear, because there are these 2 combinations which are given, that is why this is written twice. Okay. And so, this is again 1 by root 6. So, it is 1 minus 1 1 1 plus 2 by root 6. So, it is 2 and then 1 0 1 0 and so on. Okay. So, this is the way to find. Now, this is a distinct problem than the last one. The last one we had to operate by a j minus, or in some cases, as I said, that if it is in the maximal value, you will have to apply a j plus. We did not have to do anything here, because it was at the middle value. So, you had a 0 here. So, you had to do it twice. You can still do it, your m was equal to 0. If m is equal to 0 and the maximum value of m can go to 2, you have to do this twice. Instead of that, you wrote down all the linear combinations by inspection of what can be the m1 and m2. It looks a little complicated, but it is not actually. If you just sit down and sort of clear up in your mind that what are these indices for a given value of m, what are the different combinations of m1 and m2 that we can find, you can simply write it down. Okay. We have shown 2 examples. There will be more examples in the assignment, and this is how one actually finds out the Clebsch-Gordon coefficients, which, as I said, that it denotes the probability for a given j and m, that is, which are the eigen values for j1 j square not J1m, J and m, that is its eigenvalues for J square and Jz. What are the different combinations of M1 and M2 that could be there? So, if you make a measurement, what are the probabilities that you would find them in distinct M1, M2 states? M2 states, I mean M1, M2 states that are defined by distinct indices. That is what does Clebsch-Gordon coefficients physically mean. Okay. So, we will stop here for today and continue with some new topics next day. Thank you.